So in our last big differentiation rule, we're going to be talking about composition of functions. So to start this video, I want to just try and give a brief reintroduction to composition. This little circle here is our composition symbol. This means f composed with g. So let's say we have these two functions, f and g, and we want to talk about composition. When we write f composed with g, that's really f of g of x. So what we're really doing here, and maybe I'll switch some colors up, we're taking this g function, the square root of x minus 6, and it's going inside of the f function, meaning it's getting put in for x. So what we have here then is we could write it as like 4 times g of x squared plus 1, but since we know what g of x is, we can really rewrite this as 4 times the square root of x minus 6 squared plus 1. Notice that our function, before I simplify it, our function looks like 4 times something squared plus 1. Normally we evaluate these functions at numbers. Like maybe we could look at f of 1 and we'd say 4 times 1 squared plus 1. And if we were looking at f of negative 7, we'd say 4 times negative 7 squared plus 1. We can evaluate this function at another function by putting square root of x minus 6 in place of x. Here you'll notice that when we square this stuff, we're really going to get 4 times x minus 6 plus 1, and now we've got 4x minus 24 plus 1, or 4x minus 23. Cool. That's our composition function. Take a second, see what it is in the other order. Now we're switching this part up, and instead what we're doing is we're taking this f function here, our 4x squared plus 1, and we're plugging that in for x in our g function. So go ahead and give that a shot. All right, hopefully this is what you ended up with. Notice that when we take a square root of all this stuff, we can't take the square root of 4x squared and call it 2x minus root 5. That's not the way square roots work. They don't split up these sums and differences. We need this to be a perfect square polynomial. We'd have to factor it into something that could be one factor multiplied by itself for us to be able to simplify this. Anyways, there's your crash course in composition. Hopefully that will remind you of how this works. What we're going to do is try and decompose some functions. So what I want us to do is say here's f of g of x, meaning g is an inside function, and I want us to go ahead and label some options for what the f and g functions could be. There are different options for these. There's lots of different possibilities, but really there's only a couple of main ones that you guys will probably pick. So again, pause the video, see if you can write down a couple of different options for inside and outside functions, and then we'll pick it back up. All right, I think it's easiest to start with the inside function. So maybe we could look at like this 4e to the x plus 8 being inside of the natural log. So we could say g of x is 4e to the x plus 8. And the other stuff that's left over now is this natural log. And so I'll call it natural log of x, because if we're looking at f of g of x, then f of x is what we put g into, but x is in place now of the input. So it's the natural log of all this stuff, so we'll call it natural log of x. There are more options though. My guess is that a lot of you pick that, but you could also pick something like this. So we'll say 4x plus 8, and then our inside function is just e of x. That's something that you could do. You could also do something like the natural log of 4x, and then what you could say is that this is e to the x plus 2. And you're probably looking at this thinking, wait a second, why plus 2? Well, when we put it in for x, we have to do the distributive property, and the 4 has to multiply on both terms. So it'd be 4 times e to the x plus 4 times 2, which would give us our 8. Lots of options, but probably this first one is the most noticeable. In this second example, we can do a similar thing, and some people will look at this and say, oh, okay, 5 x squared minus 6 is inside of that square root, and so we'll write this as 4 over root x. Another option that you could do is you could say 4 over x, and over on the inside you could say it's the square root of 5x squared minus 6. You could also do the same kind of thing where you say this is like 4 over, here I'll switch back to green. Call it 4 over the square root of 5x minus 6. That squared has to keep going. I'm running out of space. And over here you could say x squared goes inside of x. So then you got 4 over 5x squared minus 6. Lots of options, but again, these first two are probably the most reasonable ones. All right, so that's our reintroduction to composition. And the main question that we want to ask is when we look at these composition functions, these functions like the natural log of 4e to the x plus 8 and 4 over the square root of 5x squared minus 6, how do we differentiate these things? How do we find derivatives of these functions? What you'll notice is that it's probably going to be based on what we're going to call the inside and outside functions. So that decomposition exercise that we just did is going to be important because we're going to want to look at these composition functions and pull out some options for what the inside and outside are, because then we'll use those as our parts to find derivatives of and all that kind of stuff. Now, if we look at the example, I think I wrote this up on Canvas, where we have those runners or test takers or something like that. I forget exactly what it was. Oh, it's the test taker one, I think. And you're looking at how quickly they are in relation to each other. We can come up with a pretty intuitive way of linking together these functions that are based on other functions, or these test takers that were based on other test takers. That's going to essentially motivate our chain rule. So this here should look relatively familiar, especially this part. This part is a little bit more confusing for a lot of students because these differentials are kind of tricky to work with. So let's talk about this. I think this is probably written on your rule sheet, so you can fill that in. But let's say we've got a function f that's a composition of two other functions, g and h. To find the derivative of f, notice that h is the inside and g is the outside. We've got g prime, so the derivative of the outside, and we've got h prime, the derivative of the inside. So h is our inside function. We end up multiplying by the derivative of the inside piece, or this du over dx. That's what our h function is, u, and so the derivative of u is really h prime. But notice that here, the derivative of the outside function, this part, notice that it still has h inside as the input. It's not g prime of x, it's g prime of h of x. So we're going to leave the inside piece on the inside. That's something that we're going to kind of get to in a second, and I'll try and use some helpful notation to kind of keep this in line. The other thing to notice is that these derivatives, g prime of h of x and h prime, have to exist. Or if we're looking at this notation, dy over du and du over dx, these two derivatives. If they don't exist, then obviously this dy over dx or f prime doesn't exist. So in this one, notice that these two variables are the same, u. So if we're looking at the differentials, this is kind of why differentials are helpful. Differentials are going to tell us what's acting like a variable here, what our inside is. So if we have a function y and we want to find the derivative with regard to x, but really y is a function of a different variable, take the derivative of y with regard to whatever this inside part is, and then take the derivative of that inside part with regard to x. That's a little bit confusing, but I'll explain that in a second. I think the easiest way of getting into this is by looking at a short example that we can go through step by step. So this is our general process, and what I want to do is work through this example in the same way. When we identify an inside function, I'm going to identify it with a box. I think it's easiest to just put a box around whatever we're looking at. So if we go back to our natural log one, I'm going to take that first, probably most obvious one. My guess is that most of you picked this as your inside function when we were doing the decomposition earlier. If not, no big deal. But when we do this in a class with like 30 students all face-to-face, it ends up where like 20 of them are going to pick that 4e to the x plus 1. Or if we did it with like, 8 groups, it's something like 6 or 7 of them pick that first as the inside piece. So not everybody, but we're going to build up our intuition as we go. I'll explain later how to tell what's a good option for the inside. Anyways, so we're going to identify that first. What I like to do is I like to just rewrite this with that box empty. So we want to find the derivative of the natural log of the box. What I'm doing is this variable substitution where they say u is equal to h of x. I'm setting that equal to a box at first. The reason I want to do that is because I want to just focus on the outside function first. What I want to do is find the derivative of the outside. And now here it says evaluated at the inside function. What that means is we're just going to not worry about the inside part for now, and we'll put it back in place later. So think a little bit about what the derivative of the natural log of a box is. Now, this is real weird because we're used to looking at the derivative of the natural log of x. But notice that the box is just taking place of x. So normally, the derivative of the natural log of x is 1 over x. But now our variable isn't x, it's a box. So 1 over the box. Then we got to multiply by the derivative of the inside, which our inside is box, so I'm just going to say box prime. And now we can fill that all in. We can say our box was 4e to the x plus 1. And the derivative of that box, the derivative of the inside part, is just 4e to the x. So we can combine all this together and get 4e to the x over 4e to the x plus 1. Couple of things to notice. First, the inside portion is inside of the derivative of the outside. That's a very strange sentence, so if you want to pause it, go back and replay it a couple of times, that's fine. But notice that it's not 1 over x for the derivative of this natural log function. It's 1 over all the stuff that was inside of that natural log. That stays the same. We don't change the inside portion when you're dealing with the derivative of the outside. The only time we take the derivative of the outside is when we tack it on at the end. We multiply it at the end because we're dealing with this chain rule thing. Now, I don't have a proof of the chain rule in this video. I'll probably throw one up on Canvas so you can see it if you'd like. But I think that intuition with the test takers is good enough. We have to multiply these two rates together. So we're going to multiply the derivative of the outside with that 4e to the x plus 1 still in there, and 4e to the x, which is the derivative of the inside function. So we kind of link together these derivatives. We do the outside first, and then we just keep moving our way in, and we say, okay, then take the derivative of the inside. All right, if you want to stop and replay this example a couple times, that's fine, but let's start looking at some other ones. Here's 2 examples that we can look at to try and figure out what's going on with all this stuff. When we look at the derivatives of these functions, the first thing that we're going to want to do is identify the inside pieces. So what I would do is encourage you to take a second, and before you do anything, just go ahead and put a box around your inside piece. Notice for the second one, I rewrote this using a -half exponent instead of having it over a square root. I think that's easier to see. We're used to doing that if it was like -1 over the square root of x. So let's keep doing that. Whenever we see square roots, we're going to try and convert it to exponents. It'll be helpful. Anyways, go ahead and put a box around your inside pieces. See if you can identify what we've got. All right, here's our 2 inside pieces. The inside of this we're going to call x squared minus 5. Because that's up in the exponent on a function. And the inside here is going to be 6x minus 2. It's pretty easy to tell when you convert it to this exponent because all exponent type things are going to work the same. If you've got something in parentheses raised to an exponent, pick the stuff in parentheses as your inside piece. That's a good, easy rule to use, and I would say it's probably more of a strategy than a rule because things can change a little bit. Things can be different. All right, so for these two examples, I'm going to rewrite them with an empty box just so it's easier to visualize for us. So we're looking at the derivative. Actually, maybe I'm going to write it underneath. Let's put that over here just to give us more room later. We're going to look at the derivative of 3e to the box. What that means is that we've got a regular exponential as our outside. So think about what the derivative is of something like e to the x. But now notice we don't have x here. We've got a box. So this is going to be 3e to the box. And our chain rule says multiply by box prime. And now you can just start filling in what's in the box. Our box is x squared minus 5. So let's put that in place. And the derivative of that is a pretty easy 2x. At this point, you're going to try and just simplify as much as you can. We've got a bunch of multiplication here, right? So let's go ahead and take this 3 and this 2x. Let's multiply those things together. And we've got 6x e to the x squared minus 5. That's our derivative. What you'll notice is that this kind of looks like that rule with no explanation that we had. The rule with no explanation, if you remember, was something like, maybe I'll just do this up in the corner. It was something like if we had the derivative of e to the, to the 2x, we said that was 2e to the 2x. Notice now that this is just our box, and this one here is box prime. So this is really just a chain rule. So the rule with no explanation is nothing more than just a really small chain rule. So don't worry about having that thing memorized as a separate thing, because it's just this chain rule. If we do it with boxes and box primes, you'll get the exact same thing. All right, over here, we've got negative box raised to the negative half. Oops, and we want to find the derivative of that thing. I forgot my little differentials out front. Let me fix that. There we go. So now we've got an exponent. What we can do is bring this exponent out front and subtract 1 just like normal. So when we bring it out front, we're going to end up with positive half now, because that negative sign offsets this negative. Box raised to the negative half minus 1. That's negative half minus 2 over 2. So that's negative 3 over 2. And now we need to multiply by box prime. So let's go ahead and fill things in. Our box was 6x minus 2, and the derivative of that is 6. At this point, I can start rewriting things. I've got a negative exponent, so I'm going to go ahead and put that whole thing in the denominator with this 2. I've got a 6. That's really 6 over 1, though, so 6 is in the numerator. So I've got 6 over 2 times 6x minus 2 to the 3 halves. Or we could really just say that's 3 over 6x minus 2 to the 3 halves. And that's our derivative here. All right, one more example. We're going to find the equation of a tangent line here. Remember that for this, we need the derivative. So we need the derivative because we're going to use that to find the slope of the tangent line. And then we have an x value, we need a y value. The y value, if you remember, is just our function value of 2. So before I even do anything, I'm going to go ahead and plug 2 into my function and see what we get. 2 squared is 4. Half of 4 is 2. 2 minus 1 is 1. So this is really 1 to the 5th, or 1. All right. Go ahead and find the derivative of this. Pause the video, see if you can find the derivative, evaluate it at 2, and then put things together, and then come back and see if it matches up with what we're having here. All right, so our box in this case is going to be half x squared minus 1. So now I'm not going to rewrite this blank. I'm just going to look at this and say, okay, the 5 is going to come out. And so we'll say f prime of x is going to be 5 times our box raised to the 4th. Maybe I'll make that box a little bit bigger so I have some more room to write in it. There we go. That's going to be raised to the 4. So here we're bringing this exponent out front and subtracting 1. And now, because we've got chain rule, I'm going to multiply by the derivative of the inside, which is box prime. All right, so fill things in. Here we've got half x squared minus 1. Notice this is a set of parentheses raised to an exponent, so we can't multiply that 5 in there. But if we bring down the 2, we end up with 2 times half, which is 1, times x. So we just end up with x. So here we've got 5x times half x squared minus 1 to the 4. All right, all this to say we want to figure out what our slope is. So we're going to say m is equal to f prime of 2, which is 10 times half times 4 is 2 minus 1, that's 1. So this is 10. So all this to say we've got y equals m times, maybe I'll do it like this. I'll just start writing it in. 10 times x minus 2 plus 5. That's 10x minus 10. That's going to be, or sorry, that's wrong. 10x minus 20 plus 5. I should do multiple steps here. So that's really 10x minus 15. So there is our tangent line. If you wanted, you could also go ahead and do y equals mx plus b. Plug in 2 for x, 10 for m, and 1 for y. Oh no, I did things wrong, didn't I? Look back at this. All right, let me fix this. Sorry. Our y value is 1. I think I looked at this 5 exponent here and put that in here, plus 5. That's supposed to be a plus 1. Sorry about that. So now this here becomes a negative 19 instead. I'm glad I found that before the end of this video. But now, again, you could put in 10 for m, 1 for y, and 2 for x, and solve for b, and you better get negative 19. So feel free to go check that out, but either way, you get this equation of your tangent line. So we can do all of the normal stuff with our derivatives here. We can find slopes, we can find equations of the tangent lines, but the key is our chain rule. We need to identify an inside piece so we can kind of move from there. Now, my hint to you, I'm going to go back up to this part here when we were identifying different insides and outsides. My hint to you is to try and pick it so that your outside function is as easy as possible, while your inside function is as well. So for us, I might look at this setup and say, all right, I know the derivative of the natural log of x. Well, really, that's going to be the natural log of the box. And I know the derivative of 4e to the x plus 8. In this one, I might also pick this first one, because here, that's really 4x to the negative half, or 4 times the box to the negative half, and I can go from there. Notice that if you pick this version, then you've got layers of composition here as well. There's another box inside this square root. So it's fine to do that, but what you'll notice is that you'll have to do a couple of chain rules at the same time. My challenge to you is to give that a shot. See if you can find the derivative of this function here in a couple of different ways. Maybe try it this way first, and then try it this way after that. That might be kind of interesting to see what's going on. That's all we've got for the chain rule. I know this is a long video, but this is probably our most difficult setup for this derivative rule. The nice thing is that our intuition is going to start kicking in. We're going to get pretty good at all this decomposition stuff. And so what you'll notice is that once we get good at that, the actual derivative rule isn't so bad. When we're doing this part, putting in our box and our box prime, it's not going to take that long. The quotient rule is going to take long in terms of like memorizing that bulky formula and plugging things in. So with the quotient rule, there's more work later when you actually use it. For this one, the chain rule, there's more work setting it up, finding this decomposition, or you could say finding the g prime of h and h prime. Other than that, though, this is all we've got. So take a look at all this stuff, get comfortable, try a bunch of these examples, and if you've got any questions, let me know. Good luck, everybody.